Yeah, thanks for giving me the occasion to speak here and for inviting me. So I predict this is by far the easiest talk of the whole conference. And it's so easy that I can give essentially the full main statement on the first page. And I haven't been in this lucky situation for many years. So, I mean, common wisdom in symplectic geometry, I think, is that we choose an almost complex structure, tame almost complex structure, and then we look at curves, and then we have lots of functions on the curve, but we have essentially no functions for a general almost complex structure on a variety, on a manifold. Nevertheless, in thinking about how to connect Mark's and my work, and together with Dan Abramovich and Sheila Chen on punctured and logarithmic Gromov-Witten invariants to the symplectic, I mean, to compare it to certain symplectic objects, I started to think about how to get our favorite picture that makes the algebraic theory so clean and so easy, conceptually so clean, I think. It's in my head. How to kind of mimic this in symplectic geometry. And I could do it. I mean, because in the end, the situation that we work with is algebraic, and we have lots of functions. And then I just do something away from the divisor, and that will be always symplectic. But in a way, it's a little ugly, because then you still want to say, hey, what I compute are really symplectic Gromov-Witten invariants and so on, right? So and then I went back and thought a little bit, and why do we actually not have these functions? And I got more optimistic. And after many turns and so on, I came about, thought I have a proof of the following theorem. And together with Yuan Yao, I kind of, after many iterations, we made it work. So the statement is, let's say you have a symplectic simple normal crossings divisor. So that's a union of symplectic submanifolds intersecting positively. And then after an perturbation of your symplectic structure, keeping the cohomology class, there exists an omega prime tame almost complex structure such that D is actually J-holomorphic. And that might confuse people by J-holomorphic. I do mean not just that it's an almost complex submanifold, it means it is locally given by the zero locus of J-holomorphic functions. And we can characterize such a path-connected space of such J. I don't know if the space of all such J is connected, of tame J. I actually don't believe so, but that's not relevant. We have a certain subspace that we can characterize that is connected. So we can do symplectic invariants using the structure. So let me, for clarity, so we have this hierarchy, and let me also explain how this relates to previous work. So easiest level is, of course, to just have these symplectic SNC divisor. And then you could ask, well, is there maybe an omega tame J making all this D an almost complex submanifold? I mean, all the divisors. It's actually unclear to me if that is known or not. And curiously, Tirani, McLean, Zinger have this wonderful and involved work where they prove that this can be done after perturbation, but they somehow never I mean, they must have thought about it, and I didn't ask them what they found. But I think this is in some way maybe still not known. I don't know. So what Tirani, McLean, Zinger did is they provided a regularization. What they call regularization will be featured in our proof. So again, there will be a symplectically isotopic omega prime, and then there is such a J such that D is J almost complex. And that is enough if you want to cook up a theory of symplectic log Gromov-Witten as Tirani has done and Elena Ionel has also done. And but that is in a slightly more involved picture, I think, than what I'm going to do. So, and part 3 is the result I was just stating. So, and Tirani, MacLean, Zinger imply this part 2.
Trying to give it next week, so I think I did.
Okay, very good. Okay, so what I really want to do has nothing really to do with this result, but this was the context of what I've been thinking about and how I want to why I've been thinking about these pseudoholomorphic divisors. It's a version of a logarithmic Pionicon Solomon-Schwarz map that is an important ingredient in my project with Tim Perutz to prove homological mirror symmetry for or BS mirrors or maybe even intrinsic mirrors. So we would start with an SNC degeneration of Calabi-Yau's. So these are proper Calabi-Yau's. I don't know how to do the Fano case at the moment. That would be more along the lines of what Daniel Pomigliano has been doing. So we look at this degeneration, and then we have the general fiber is a Calabi-Yau manifold, a closed Calabi-Yau manifold, and we have a symplectic monodromy by going around the origin of M. That's a symplectic transformation, symplectic isomorphism, automorphism T. And then we can build 2 rings from this. One is this intrinsic mirror ring I've been building with Mark, and the spec will be then a mirror candidate. And that has one generator for, well, the B will be a dual intersection complex of the central fiber, which is a divisor, right? And then it has an integral structure, so you can talk about 1 over D integral points. And it's this graded ring, so for each 1 over D integral point, you get 1 generator, and then I have some base rings that I'm not going to discuss. That has to do with curve classes. And then on the other side, on the purely symplectic side, you can build a ring from the symplectic monodromy that Tim educated me about, which is simply this Floer theoretic symplectic monodromy ring. So for each D, for each iterate of T by D, you get one group, and it has a pair of pans product, and that's a nice ring as well. And then the log PSS map should be a homomorphism in this direction. So that should contact, and the statement would be there's an isomorphism, and that should be a very, very general statement. So this would give a purely symplectic construction of the intrinsic mirror ring also. Okay, so and then to prove homological mirror symmetry, we would do some automatic generation for this with Floer theory that is not part of the topic here. So, but that's the context that I was interested in. If you think about this morphism, there have been similar things on the screen. So what you would count is, of course, there's the input is something that inevitably contains logarithmic context because it has to make contact to what Mark and I have been doing. So there's some very, very kind of singular stuff on the central fiber where we use logarithmic techniques. Well, then you have this, I mean, essentially we complete this, spread it out symplectically to the whole complex plane. And then at infinity, you would have this kind of Floer theoretic symplectic monodromy stuff. And so, and then you look at multi-sections of that thing that on the central fiber can bubble off some logarithmic stuff, and at infinity you would have Floer theory. So this is a picture where I inevitably have to mix the symplectic and the logarithmic picture, and that's why I was interested in looking at this. Okay, so what are the other motivations? There's another project with Dan and Mark, where we want to generalize this intrinsic mirroring, which is really something like a the cohomological degree 0 symplectic cohomology ring, or relative quantum cohomology ring in cohomological degree 0. Okay, so to speak, just for points to a higher cohomological degree. So that would couple your cohomology that has some bulk classes that live in the interior of X minus D. And then there's some stuff that lives on the boundary, which is kind of a real law of D, and that would would couple with quantum cohomology, and what we with a quantum product. And what we noticed is that doing this, unlike the cohomological degree 0 part that we did in the intrinsic mirror thing, we can't work cohomologically. We have to work on a chain level. So there are differentials coming in, and they bring in chain level stuff. So that requires some kind of deviation from the standard, maybe Bernd Siebert approach to virtual fundamental classes that we have gotten used to in algebraic geometry. So again, that requires something, and I will use global Korenishi charts in some way, and some regularity that where it's also kind of, you will see that it's kind of much easier to work once I have the full picture that we have in algebraic geometry. So as a related topic, if you want to do symplectic log and punctured Gromov-Witten invariants and compare it with the algebraic geometric world, it's good to have something that is as close to the existing algebraic geometric world as possible. And Muhammad Tarani and Mohammad Swaminathan are working on this as well from the slightly different point of view of Tarani that requires us less regular, less special, almost complex structures. And then I think it's also, to get an exploded manifold, I think Brett Parker is secretly assuming you have something like an almost complex structure where your divisor can actually be written down as a zero locus of a divisor. So it might give some further kind of validation of Brett Parker's work, who I'm always been very kind of impressed with. And then ... I don't know. I mean, my fantasy is limited. Hopefully some symplectic geometrists will come up with some other things. And hopefully it will also help to deal symplectically with normal crossing situations in a simplified fashion. So a lot of the machinery of algebraic geometry or complex geometry just relies on the fact that you can write it as zero locus of a function. Well, now we have the function, so whatever we can do, you don't have to do anything, invent any new machinery, just push the button. Okay, so let me first say a little bit, some trivialities on J-holomorphic divisors and line bundles. Essentially, this slide is, everything goes as you expect, but let's spend a minute to convince ourselves that it's actually the case and where there might be some pitfalls. So there's an obvious notion of a J-holomorphic line bundle. So that would be, you could either define it by saying, well, it's a line bundle where the transition functions are J-holomorphic, or equivalently, you could say it has a 0-1 connection. So meaning a del bar operator, so del bar lower J, which admits local J-bar J-holomorphic frames. And then, of course, these are equivalent, the usual way you would think. Of course, you have to be careful, del bar J squared won't be 0, okay, in general, but I don't care for this talk. Now, you obviously immediately see that if J is general, any such J is trivial. It's simply because whenever you have a local J-holomorphic function, the rank of the 9-host tensor goes down. And for general J, it's just full rank. So there are no local J-holomorphic functions. And any such L, well, I said trivial, that's not quite true. What I meant is kind of flat. Yeah? So it's coming from a flat structure. And then there's this usual 1-1 correspondence between J-holomorphic divisors and J-holomorphic line bundles with a section, with a transverse section, okay? So let's first do this just for hypersurfaces. So you would cover D where these local neighborhoods where you have a local function. You take these to define the transition function. You have to prove that any two such J-holomorphic functions actually differ by an invertible J-holomorphic function. That is true. And then you get the 1-1 correspondence. So to distinguish it from the algebraic geometric world, maybe just for my own sanity, I'll invent a new symbol. I'll write it LXD instead of OXD. Okay, so whenever you see an LXD, you should think OXD, but in a pseudoholomorphic world. And you should note that when you have this kind of one-one correspondence, these functions really exist only very locally around D. So away from D, you can still have a very general, almost complex structure, and the transition function would just be constant 1. So on X minus D, this, just as in algebraic geometry, right? This Lx of D, now I wrote it wrongly, right? So I promised I would write L. This Lx of D is just trivial, plainly trivial, okay? It could have more sections locally, okay? But the canonical section is just constant 1 in the distinguished trivialization. So once we have this, we can easily define symplectic log geometry. Okay, again, that has been a bit of a headache thinking about it for many years, because all these notions kind of depend on some notion of functions. So I've been freaking out people for many years in giving like starting talks with a log structure is a homomorphism of sheets of monoids and blah, 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 you know. And then given Talbot said, what do you mean? And he wanted, of course, a more kind of intelligible definition. So I think the one, there's a more geometric way, and had I been aware of it some years ago, I might have taken that approach to present log geometry to symplectic geometers. But it's around for a long time. The Deligne-Faltings, it goes by the name of Deligne-Faltings log structures. And it starts with this, still a bit of a mouthful, constructible sheaf of monoids and bar. But in, let's say, a simple normal crossing situation, it's something very simple. You just take a copy of the constant n sheaf for each irreducible component, takes a direct sum. So M bar is like the sheaf of vanishing orders of functions, which have zeros at most along D, okay, containing D. And then, then locally you have sections of U, of M bar, and these give a pair of a line bundle with a line bundle on U and a section of the line bundle, okay, on U. And so this is the structure. And then you need various compatibilities that you could, in a highbrow fashion, say it's a symmetric monoidal functor between certain categories that I'm not going to introduce, okay? But morally, you should think, of course, in an algebraic geometric situation, if you have a normal crossings divisor, this L is just this OX of DI, right? Or OX of some AI DI. And then these compatibilities are captured by saying that has a chart and blah, blah, blah. Okay, so if I have, so now it should be obvious, hopefully, that if I have a J-holomorphic SNC divisor, I can define a J-holomorphic log structure in this language, which would say I take a sum AIDI, which would be a section of M bar U, okay, over any, it's even working globally, right? We have SNC. And I take these corresponding line bundles that I just introduced with the canonical sections with zero loci DI, and takes the powers AI, and then takes a tensor product. And this guy has a canonical section. It's a tensor product of the corresponding canonical sections of the factors. So far, so good. Any questions? All trivial, hopefully. Okay. Oh, it's, yeah, I wanted to mention that thing. So incidentally, just last November, Mohan and Mohammed brought out a paper, posted a paper in the archives that kind of spells out all of this in the kind of, in a way that is kind of, I think, designed for symplectic audience. Okay, so it's essentially just spelling out what it is and then saying how Tirani's work fits into that framework. Okay, so of course Tirani wouldn't have these kind of, that wouldn't be a J-holomorphic divisor, right? So you have to be a little more careful what they are having. Okay, so then let's come closer to the thing, to kind of symplectic Gromov-Witten theory. So let's first get a little bit of a connection to one very central device in all of our theory, in Gromov-Witten theory, the theory of Artin-Fans. So there's this complex analytic stack. I mean, typically in algebraic geometry, of course, it's just an Artin stack, but here in this context, we work analytically. So you take the complex line and divide out C star. And I write A1 in GM to make clear it's not C star, it's not just C minus a point, it's a group. And A1 is really has a vector space structure. Okay, so I take this quotient, and that classifies GM bundle, GM torsos in the following way, or as holomorphic line bundles with section. So you test the stack by some, let's say, complex analytic space, W to A1, and then you have this line bundle over here. I took a dual. There is a little bit of a sign confusion, so they're all equivalent or anti-equivalent, so it doesn't really matter, but the section would go in this direction, right? It's a morphism from A1 to L. So if I want to say it has something to do with L comma S, I better transpose the whole thing, and the section would give this morphism. So I have a GM equivariant diagram up here, morphism up here. So GM acts here by the usual bundle multiplication. And this is a line bundle, so kind of one compactification of a GM torso by the zero section. So this is how this stack classifies such diagrams, or how this stack is the same as the stack of holomorphic line bundles with a section. Okay. So this is complex analysis or algebraic geometry. If we are in a J-holomorphic world, I can now say, similarly, I can look at J-holomorphic maps from an almost complex manifold to A1. Well, so first let's spell out what this means to have a morphism to a stack. It means that locally it factors over a chart of the stack. So that would be a holomorphic submersion from some space to A1. Well, we have a nice holomorphic submersion here, namely it's just the A1. So we would locally factor this over this A1, and then of course I know what a J-holomorphic map is, right? So of course that's all trivialities, right? I'm just saying a holomorphic divisor is the same as giving local J-holomorphic functions, right? This is the same thing as saying I have a morphism xj to A1. But this language is useful in spelling out some things that are going to come. So that's what I just said, right? So a J-holomorphic divisor. Okay, you can argue about this. This is not quite right? So maybe I need a smooth thing here. Sorry, maybe I need to smooth. Maybe smooth submersion. Okay, submersion. I have to be careful with the word smooth. Okay, I want to use smooth in the sense of C infinity in this talk. Okay, not the smooth in algebraic geometry. So submersion. Similarly, if I have an J-holomorphic S and C divisors, then again, this should be a submersion. It's given by locally by a submersion from X to AN, which is the n-dimensional analog of A1 mod GM. This doesn't hold globally, okay? And this is where these Artin-Fans come in. So let me try to show this in an example. So before reading the first line, maybe read the second line. So let's look at something like this normal crossings divisor with two components, but also two intersections in two dimensions. So I get these Artin-Fans at each point, right? So at general points, it's nothing. It's just a point. Then at general points of the divisor, it's an A1. I get two copies of these. They are all identified, essentially. And then here I have two copies of A2. But they don't really talk to one another. I mean, they talk to one another along the D1s, but not at their centers. So this means you have to patch these things together by open embeddings. So the other confusing thing is this looks like the coordinate line. No, it isn't. It is the complement of a coordinate line divided out by GM. Okay, so this is an open embedding in A2. These are all open embeddings. So point open embeds into A1 and so on. Okay, all a bit confusing. But you patch this all together. So you should think of take something like A2 minus the coordinate axis, glue it to A1 cross A cross GM to GM cross A1 and then to the whole thing twice. Okay, so it becomes a somewhat and then you divide out GM squared. So it becomes a somewhat non-separated thing, and this is what this Artin fan is. Okay, and it's a natural repository of log structures on that space. So you take the co-limit of all these things, and that is I should maybe write it a sigma. I'll explain the sigma in a second, or interchangeably curly x, which is easier to write. So what is a sigma? So what you observe is the interesting thing about this is it looks like you would need to know x to build it, but you don't need to know the whole of x. The only thing you need to know is the dual intersection complex of your divisor. So whenever you have a simplicial complex, you can actually, or maybe generalize the simplicial complex, simplicial delta complex, or whatever you call this. You can build this Artin fan. And so it only depends on this kind of discrete information, the intersection pattern of your divisor. That is sounds almost like a defect of the theory, but it's a feature in the sense that it is a lot more universal. Yeah, it's discrete. It's a discrete enrichment of whatever comes after or comes before. Okay, so now I can say a J-holomorphic SNC divisor with dual intersection, with a given dual intersection complex sigma is the same as a J-holomorphic submersion from X to A sigma. When did I start? Okay. Okay, so if we have all swallowed that, then it's very easy to say what a J-holomorphic stable log map is. So we have given this normal crossing situation that gives me this morphism to the Artin fan, where the axis is what I previously also alternatively called a sigma of x comma d, the dual intersection complex of this divisor. And in previous work, with Dana Bramowitz, Gila Chen, and Mark Rose, we showed that the space of log maps from C to this curly X, slightly uncomfortable to think about. So this is mapped to the Artin stack, but if you unravel it in terms of line bundles, it becomes something extremely trivial. So it's essentially a domain, yeah, with a nodal curve, with its kind of natural system of line bundles that come from the nodes and the marked points. Okay, so there's a system of line bundle that comes from it. It's called the basic log structure. And then it has only the kind of very discrete information in what's happening on the M bar level, and which is captured in what's called the tropicalization. The tropicalization is the kind of dual of that. Okay, so if you know that, so these log maps is the same as giving this kind of log structure on C, together with this tropicalization. That's all it is. It's really a discrete enhancement of this stack of nodal curves of genus G with k-mark points, not more. So it has the same dimension. Nothing fancy geometrically is going on. It's locally really one is the same thing up to some tropical enhancement that has a kind of discrete flavor. So this means we have this diagram here, okay? That's important. We don't have to do any extra work. That already exists. We also have that, okay? So then I can pull back that submersion to this space. That's all algebraic geometry. So you get this smooth space XC over C. It is smooth, okay? The fibers are just kind of this some product of the strata. So if you have a point here, it's a product of the corresponding stratum with the GM codimension of the stratum. So then what is a J-holomorphic stable map? Well, this is all holomorphic, but this comes with a fiberwise, actually not only with a fiberwise, it comes with a almost complex structure that is induced from the J here and the C here, okay? So I assume I have a J here maybe. And then I can pull it back to some J tilde, and I can ask, when is a section of this, so let's take a fiber here, let's call it C. This is this C. It's a fiber of this map over some little point S in M, and frac M. And then I can ask, when is this section holomorphic? Okay? And that will be my J-holomorphic stable map. So a J-holomorphic stable map, log map, log, of course, will be a J-holomorphic section of this diagram. What do you mean? Say it again. No, this one isn't. So wait, this thing here is all algebraic, okay? This one isn't. But this map is smooth. This is an algebraic stack. This is this guy. Oh, sorry, maybe I should have written M of X here.
X is not algebraic.
No, but the curly X is always. Curly X was the, right. Yeah. So I start with this guy, I get the sigma of X, I get this one, and then this is algebraic geometry. And up here we are not safe, right? I mean, the two of us, many in the room are safer than us, but okay. So yeah, let me spell this out a little bit, right? Because I mean, of course, we could go home, right? If we are very comfortable with working with stacks and believing everything, but I wanted to be careful that I'm not making any mistake with claiming there's a J tilde and what does it look like and so on, right? So let's look at this, let's spell it out, okay? What are the equations of this guy? So locally, the X will look like U cross AR. So I get at a codimension R point of a stratum of D, right? Codimension R point of D. It will look like Z, and U is a manifold, okay? And then saying I have this morphism means I factor locally over AR, and AR has this submersion to curly X. It's a local model of the things I wrote down before. And similarly, I test it, let's say, with the C analytic space, S to X, okay? And this is all I will ever need, interestingly. I could also work almost complex, but actually, in the end, I will always only need that map for actual complex analytic spaces. So this is harmless. So we have this map G and F here, these maps. And then the fiber product, S cross curly X with usual X, is actually isomorphic to a product of S with GM to R with U. Okay, so it kind of cancels that thing and replaces by a GM to R. And the equation looks like this. So it's triples SHX such that F of X is H times G of S. H is this group element, acts on AR, right? So very simple equation. And yeah, that's what it is. Let me see, F of X. I think I made a slight mistake here. The X has a U factor. No, this is fine. No, I think it's fine. Okay. Denis? Yeah, okay. Okay, so what this also shows is the expected result that Tirani, McLean, Zinger showed in their framework, but here it's kind of also very easy to derive from this equation, that the relative tangent bundle from X over curly X is a logarithmic tangent bundle. So it's really given by these kind of Zi, dzi, if Zi are defined that the components di of the divisor locally. And the Del-Bar-J equation for these sections, of course, take value in the relative tangent bundle. So there is, of course, some Del-Bar part, but because we have sections, that is trivial. So it's really a map from C to XC, and it takes values in this for such a section. The del bar J equation takes values in the pullback of this relative logarithmic tangent bundle, and it turns out it's actually analytically totally harmless. Okay, so whatever is already in whatever your favorite gluing framework is, it's not any different here. Okay, so you have to change your exponential map slightly, adapt it to this relative situation, but the analysis just means you wiggle your almost complex structure slightly, and people have done for ages. Okay, so there's nothing fancy going on in terms of the analysis. So okay, so now I want to spend maybe 3 slides to give you an idea why you should believe the result. I already mentioned that for general almost complex structures, any J-holomorphic is locally constant. So, and for such J, any J-holomorphic L arises from a flat connection. So, and whenever you have a smooth J-holomorphic divisor, you get a J-holomorphic structure on the normal bundle. Okay, so it's not only that you need a function kind of locally, kind of normally, it kind of percolates down to the deeper strata. So if you have these J-holomorphic functions defining even a smooth divisor, you would also get something J-holomorphic, namely the transition functions for this ND over X. Okay, so that can make you a little bit nervous, but that's just a matter of life, right? So on any stratum, whenever we have this, actually I don't even need that. So this will give functions that have sections, but I have from the transition function I have anyway I have many it could be holomorphically trivial. Okay, so maybe I need the statement. So whenever it's topologically non-trivial, this line bundle, I also need to have some non-constant J-holomorphic functions. Okay, so for the construction, the basic idea is the following. I have this SNC divisor. I take transverse hypersurfaces, H0 to HR, constructed by the methods of Donaldson and refined by Wu many years ago, in such a way that the homology class di is a difference of hi minus h0. Okay, and then the basic idea is simply that I write this normal bundle of di in X as an Lx of hi tensor Lx of h0 dual. Okay, so that gives me a J-holomorphic structure on the normal bundle. I use an exponential map to extend. To make this consistent over various strata, I use this TMZ regularization that I already mentioned. So this means it looks like this. You get these boxy neighborhoods, right? Or rather, each di comes with a neighborhood, and the intersections of the neighborhoods give you these boxy neighborhoods of deeper strata, and it's all compatible. Okay, so here you will have a rank 2 normal bundle that splits naturally into the direct sum of these 2 normal bundles, and the exponential maps there are compatible. That's what a TMZ regularization is. Okay, as long as the list is, when you look at the paper, it took me a while to understand what it really means, but it's something in a way. If you want to sit down and write it down, it's okay, and it's exactly what you have to do. And there's also, of course, some compatibility with symplectic structures that I'm kind of sweeping under the carpet. So this is the idea, right? I just mentioned. Yeah. So I take the J-holomorphic structure on this normal bundle by LDI. Slightly hard to parse now. I take the intersection of di with hi. Hi was transverse to di, so that becomes a divisor in di. So this makes sense on di. And then the same thing with H0. And it's topologically right thing, so it's isomorphic to your normal bundle. That gives you a J-holomorphic structure on the normal bundle, and you push forward to a neighborhood of D by TMZ regularization, and then use tameness to extend it to everything. Okay? So, of course, you have to be a little careful to make this all tame. But worse, the whole thing is, of course, there's some inductive process. So first, you see, I also need that HI is in DI a divisor, okay? A J-holomorphic divisor, otherwise the whole thing fails. So we rather need to regularize the union of all these things. So the picture I had before, like not only this, but there will be some more divisors coming in, transfers to everything, and these HIs, and then repeat inductively. So to do that inductively, actually, R+1 divisors are not enough. You need a bunch more, okay? So you get this double index sets HI mu. They're all homologous for when you vary the mu's, okay? And then you have to be very careful to make the choices of divisors and isomorphisms compatible, okay? Consistent over all the induction and the strata. And that took a while to sort out and even longer to convince Yuan that everything is all right. Okay. Let's see, how am I doing time-wise? I have like 15 minutes left or something, or 20, maybe 15. Yeah, it will be hopefully be done a little earlier. Nobody will complain, I guess, with 7 talks this day. Okay, so this is the result. So now I want to spend maybe 2 or 3 more slides on telling you how to then easily get to log Gromov-Witten theory using global Kuranishi charts introduced by Abu-Zaid McLean-Smith, and in the version presented by Hershey and Swaminathan, where they use this rel C infinity framework that I've found a little easier to work with. Let's put it this way. So this is just this diagram, okay? So let me just explain the notation. This is the space we are interested in. So this has a J, right? So there's an M of xj. These are my J-holomorphic stable logarithmic map for this normal crossing situation x, d. Sorry, this is a typo. What am I doing here? This is, of course, not MGK. This was the M of curly x. Oh, no. Sorry, I'm presenting everything good. No. This is I confused myself with the slide. This is just recapping what I was at McLean-Smith and Hershey Swaminathan doing. So let's do the ordinary Gromov-Witten case. No log here. So here the base space is an MGK. That's just genus G K-mark points, nodal curves. And then they have cook up a B, a manifold that maps here submersively. This is our stable map moduli space. And then we have the thickening, which is a submersion over the thickening of the moduli space of this, well, it's not the thickening of the moduli space, it's a kind of G-enhanced thickening of the moduli space. We have this bundle E, everything finite dimensional, and with a section and the zero locus in it, it can be awful, right? But it has a good fundamental class. And then everything is equivariant under a compact Lie group G. Okay, and then the quotient by G is a moduli space. And that's enough to cook up a virtual fundamental class on M of X. So the cool idea of Abu-Zaid McLean-Smith is to kill all the automorphisms of your domains, which cause all the trouble, by just taking some very high degree embedding of your curves together with marked points and so on, transfers hypersurfaces into Pn, a very big Pn, okay? Very high degree, very big Pn. And then take out all the ones that are bad. So you don't want, you want sufficiently good things. So certain linearization should be surjective and so on. So this is the space, and which is just a very nice, it's a scheme, but it's a smooth scheme. That's in the sense of like really a manifold. And the T then is the usual thing, right? Some J-holomorphic perturbed J-holomorphic solutions of equations, but with these fixed domains, right? So B contains all the domains, and then you just look at curves, at J-holomorphic, perturbed J-holomorphic map from these given domains to your X, okay? And yeah, so and then you can get these global coordination charts. So this is called a global coordination chart, this whole kind of diagram here, if you want. So in symplectic log Gromov-Witten, of course, we replace, I said, MGK by this frac M of X, which is just a kind of discrete enhancement of that guy. And then we pull back by this thing. So for a while, I thought, well, we have to do something fancy here, but no. You just do the fiber diagram. This, because that guy is representable, so meaning this is a scheme, that guy here will also be a scheme. Okay, so no problem. Our B is nothing fancy, it's not a stack, it's nothing kind of, yeah, it's still logarithmic, but we don't really care. I should have mentioned that before, right? So once you have pulled back everything to this curly M of X thing, log geometry is irrelevant. You're talking about smooth sections, this traditional geometry. Okay, so this is the new definition of the base space, and that is now a complex analytic space. It's not smooth anymore. It has toroidal singularities. That's just a fact of life in log geometry, but we don't care. As we are RLC infinity over something with toroidal singularities, it's pure dimensional. That's what's count. And then you just copy what's in their papers. So the Gromov trick tells you you can trade a perturbed del bar J equation by an ordinary del bar J equation in a perturbation bundle, okay? And the perturbations, that works as in Abu Zaid, McLean-Smith, or Hirsch-Swaminathan, except you replace Tx by the logarithmic tangent bundle. Not much change. So that essentially tells you that all that's left is proving this kind of T to B, this global coordination picture, once you have an unperturbed situation, right? Because we have already perturbed, we are in a bigger space, everything is transverse, and we have to show there's a manifold. It's respectively RLC infinity over this kind of complex analytic space with toroidal singularities. So, so this is this space where you look at unobstructed stable J-holomorphic log maps. And so let's fix this complex analytics test space that will be some version of, enhanced version of this guy, right? So with the perturbation data enhanced. The target, which targets the X? No, X is smooth. The only reason I cannot work with kind of log smooth X, if that is your concern. I probably could, but I would have to think very hard of what it means to have an almost complex structure on this thing. Because once I pull back to my curly M thing, there's no difference. Yeah, this thing is just a smooth fibration over some family of nodal curves. There's no difference to the but I don't want to think about it. Okay, so right, so we want to test it here, and then we define the space of regular sections. So the only difference to the definition before is that now we want the linearization to be surjective, and then of course I have to prove the theorem that this is actually RLC infinity over this S. So kind of topological submersion, and that's a relevant diagram, right? So I have these M of, this is what I had before. I pull back to S, then I get this diagram, right? And I'm now looking at fiberwise sections of this guy. So take fibers of this over here, and then I look at sections here. Then the only difference to what's written is we need a slightly modified exponential map to take account into the kind of fact that we now deal with a smooth family over a family of nodal domains, okay? It's made me slightly nervous for a while, but it's all all fine. And then we use scale smooth gluing just as in Hofer, Wysotsky, Zehnder, just as Mohan did in his earlier work. And I think that's it. Thanks for listening.